So, last topic in Physics 20, okay? Doppler effect. Now, yesterday we were doing all this stuff with air columns and standing waves. Seemed like we were getting that, okay? I mean, we can still have a little bit of time to work on that later if we need it, but it seemed like we were pretty much ready to go. So we'll go over Doppler effect today, finish up everything tomorrow. Start final exam, well, probably we'll do unit exam review on Monday, start final exam review Tuesday, Wednesday. Okay, so we might gain a day here, okay, to have a little extra time for final exam review. So first off, we got to know what the Doppler effect is. Okay. How many people have ever noticed that when an ambulance, fire truck, police car goes by, it sounds different when it's approaching versus going away? Right? Okay, that's the Doppler effect. Okay, the Doppler effect is that we perceive the frequency of sound to change based on either the movement of the source of the sound or our own movement. Now, we already know that once a wave is produced, its frequency can't change. So this is only a perceptual change. It's not an actual change in the frequency of the waves. Okay? But it happens because of the movement of the two parts of this equation, the observer and the source. Okay? So if it's an ambulance and I'm standing on the side of the road, the ambulance goes by me, okay? As it approaches me, the siren sounds different than when it's going away. Right? And that's because as it produces sound, it's also moving. If it was stationary, then all the sound waves would be the same distance apart. But because it's moving, it produces a sound wave, and then that sound wave, if it's in front of it, doesn't get a chance to get away from it before it produces the next one. So the wavelength appears to shorten, even though it hasn't really, it appears to be a little shorter than it would have been if the object was stationary. And when it's going past me, it's the opposite. It produces a wave and then runs away from it before it produces the next one, which makes the wavelength seem longer and thus makes me think I'm hearing a different frequency of sound as it goes away. When in actual fact, the frequency of the siren hasn't changed at all. It's just my perception of it. Okay, everybody kind of follow me there? All right, so that's essentially what the Doppler effect is, but I'll let Sheldon Cooper explain it. He explains it a little better. All right, so the other thing we're going to look at here now is how is the Doppler effect responsible for the sound barrier? How many people know what the sound barrier is? Okay, so before the space program could really get going, okay, the biggest barrier was not being able to make something go fast enough to get into orbit, because there was effectively a top speed at which things could move. Right? Because every time something got close to the speed of sound, it would blow up. Okay? We would make these different kinds of airplanes, and we would put pilots in them, and they would shoot them off, and they would just get going faster, faster, faster. And then as they approached the speed of sound, the plane would start to shake, and then it would just fall apart, blow up, whatever. Okay? But from the ground, what that looked like was that the plane would run into an invisible wall in the sky. Okay? It would literally look like that from the ground level. You'd see this plane going along, see the contrail, and then all of a sudden it would just stop, and there would be an explosion, and that would be it. Okay? And so that's where the term sound barrier came from. There was something that wouldn't allow us to go faster than that. What we didn't realize at the time is it's because of the Doppler effect. If I get going close to the speed of sound in something really loud, like an airplane, okay, all the sound that I produce can't get away from me because the waves are traveling as fast as I am. Now, what kind of waves are sound waves? Longitudinal or transverse? They're longitudinal, which means they're a series of compressions and rarefactions. So what's happening is as a plane gets close to the speed of sound, there becomes a wall of compressed air building up in front of it, because all the compressions from the sound waves it's produced can't get away. They're traveling just as fast as the plane is, so they can't run away. They just build up in front of the plane, and effectively the air in front of the plane becomes so dense that the plane literally hits a wall. Okay? It can't get through it, and it breaks apart. Okay? So what they had to figure out was, well, okay, how do we get through this? The initial experiments consisted of, well, it just must be that we're not making the planes powerful enough. So they just kept putting bigger and bigger motors on the planes and just kept smashing planes and pilots into the invisible wall in the sky. Okay. In fact, they had rocket-powered planes that they were dropping out of the bottom of bombers. Okay, by the end of the program. Okay, Chuck Yeager, who ended up being the guy who did break the sound barrier, when he broke the sound barrier, the plane he was flying was basically just a rocket. Okay, it had these stubby little wings on the side and a big, long, pointy nose. Right? That was actually the thing that allowed him to break the sound barrier, was actually the long, pointy nose. But it was just a rocket-powered plane. They took him up in the bottom of a bomber, put him inside, and dropped him like a bomb. Okay, and then he just hit the switch, the rocket engine ignited, and off he went. Okay, there was basically nothing he could do after that. Once he lit that candle, he was going to have to ride that thing out. Okay, whether it meant he was going to smash into the invisible wall in the sky or whether he was going to get through. So as the flight went on, okay, they, basically the same kinds of things were happening to him as it happened to every other flight before. And so the plane started to get shaky. It started to get hard to control. His acceleration was really getting slower and slower. He wasn't able to increase in speed. He was getting right near 330 meters per second, and the plane just was struggling. And then all of a sudden, the plane jumped. It literally accelerated very quickly, and there was a massive bang. Okay? And of course, everybody on the ground went, all right, back to the drawing board. Okay, because they heard this massive bang. They saw a small cloud, okay, that very quickly dissipated, and that was it. And they're like, oh, we're screwed. Okay, that one didn't work. Rocket-powered plane, not a good idea. Okay, now we got to go and deliver the news to the poor guy's widow, and that was the line of thinking. Okay, was that this didn't work. And then all of a sudden, Chuck Yeager comes over the radio and says to him, I think there's something wrong with my Mach meter. It's jumped plumb off the scale. He had gone faster than any man in history by a factor of 2. He got the thing almost up to 2 times the speed of sound because suddenly he was through. Now, all the sound waves he was making were falling behind him instead of piling up in front. And he was riding a rocket. Okay, so suddenly he was going really fast. Okay, and he's, they only made the speedo, which he called the Mach meter, because that's all it had on it was like Mach 0, Mach 1, and then it was like, a little bit over here, because no one figured he was going to go faster than that. Okay, so he went past it, pegged the speedo, and was just, hey guys, look, I'm still alive. Okay, and he managed to land the thing, and they kind of figured out what they had stumbled upon. Okay, so essentially what happened was, if you're traveling at a rate of speed that's not really close to the speed of sound, you're going to have wider waves behind the aircraft and you're going to have shorter waves in front of it. That's natural because you're moving. But as you approach the speed of sound, the waves just bunch up. They bunch up in front, but they really spread out behind. So when a plane that's going close to the speed of sound, but not faster than it, flies over you, it sounds like a whistle or a screech as it approaches and thunder as it goes away. Okay, there's such a massive difference in the frequency of sounds in front versus behind. Okay, once you break through the sound barrier, you get through this wall of dense air, okay, then all the sound waves fall behind you. But there's a massive pressure release when you break the barrier, and that produces a sonic boom. Okay, a sonic boom is essentially almost like thunder. It's a pressure release of all this compressed air that's built up in front of the plane. Okay, now in order to break the sound barrier, you essentially have to have a plane that's shaped right. Okay? It's not about how powerful the plane is, it's about its shape. It needs to have a nose that is capable of producing a disturbance in the wall of condensed air that's piling up in front of it. It essentially needs to create a small hole that it can pass through. Okay? And the shape of the nose is crucial for that. Okay? Also, the shape of the rest of the plane is crucial. If you have, if it's not very aerodynamic, the wings aren't swept very much and things like that, then it's going to probably not get through. Okay? So that's why you see that most aircraft nowadays, even ones that are not supersonic, okay, have swept wings. Swept wings produce less resistance, a little bit more lift, okay, and they're more efficient in terms of that regard. Okay? Fighter aircraft obviously have very swept wings. In fact, some even have wings that they can change the angle of, okay, when they need to. Right? They'll sweep them back when they want to go really fast, and they'll push them out for better maneuverability when they need that. Right? Now, when you go through the sound barrier, this is what the people on the ground saw. They saw this puff, this small, very short-lived cloud that appears just as you break through the sound barrier. Because as you go through the sound barrier, you're compressing the air, and the air contains water vapor. Okay, so you've compressed all this water vapor, and if you guys remember from chemistry, like Charles' law, Boyle's law, ideal gas law, right? When you put a gas under pressure, you can condense it back into a liquid. That's what happens when you go through the sound barrier. The water vapor in the air condenses back into a liquid until the pressure is released. When the pressure is released, it goes right back into a vapor form, and the cloud is gone almost instantly. Okay? But this little cloud follows the plane until it gets through the sound barrier, and then it's gone. Okay? So that's what they saw, was this cloud. They assumed the plane had just been destroyed. All right, is that sort of making sense? All right, so once we did that, once we were able to get through the sound barrier, then the age of rockets began. Okay? And you'll probably notice that most rockets are pointy at the end and have like a little tiny, almost looks like a spear or harp, kind of on the tip of them. And that's to help them get through the sound barrier and accelerate to speeds that will allow them to gain orbit. Right? So once that was done, then obviously the space race was on. Okay? And shortly after this, okay, the first satellite was put into orbit. Okay, which was, yeah, the Russians did. It was Sputnik, okay, little basketball-shaped satellite with 4 antennas on it that went beep, beep, beep and scared the living tar out of everyone. Okay, I know it doesn't seem like it should have, but people who were in charge at the time saw that if they could put something in orbit, they could put a weapon in orbit and make it drop wherever they wanted. Okay, they basically realized at that point they weren't safe from anybody, and so that kind of began this, escalation on both sides to have better bombs and missiles and stuff like that. So, okay, so does the sound barrier part here make sense? I'm going to show you a quick video on that. It's got some footage of planes breaking the sound barrier. It sounds like it's some kids like grade 8 science project, but it's got good footage in it. I'm not too worried about what they say in it, but just about the footage. All right, so you kind of get the idea here. You get this overpressure and things like that as you break through the sound barrier. Now, when that first happened and people realized that there was this massive overpressure and this big pressure wave that would come out from breaking the sound barrier, the first thought was, okay, can that be used to break stuff? Can that be a weapon? Okay, and they were trying to figure out ways to weaponize a sonic boom. The problem is that any pressure release like that dissipates really, really quickly. Okay, there's Mythbusters did a whole episode on if you could break all the windows and glass stuff in a house. If you flew a plane over it and broke the sound barrier right over the house, would it break all the windows, break all the dishes and everything like that? And what they found is absolutely not. Okay, the pressure is released so quickly and it dissipates so quickly that you really can't unless you are right on top of it. So the U.S. Army did a bunch of tests where they put dummies in trenches, and they flew planes over top of the trenches and had them break the sound barrier as they flew over. Now, not to say that that's not going to hurt people. I mean, if you have a sonic boom really close, you could shatter your eardrum. Okay, but beyond that, it wasn't like flinging people out of the trenches and things like that. Okay, it just wasn't practical for use as a weapon for that reason, but also because you had to fly so close to the ground, you exposed yourself to small arms fire from the ground. It just wasn't a practical thing to do. All right, so with the Doppler effect, okay, like we were saying here, okay, if the plane, or if the train in this case, is stationary, then the sound in front of the train and the sound behind the train sound exactly the same. A person behind a person in front hear exactly the same tone or frequency of sound. If the train is moving, then people in front of the train hear a higher frequency of sound because as the sound is produced, it doesn't get as far away from the train as it does when the train is stationary, so the waves seem bunched up and seem to have a shorter wavelength and higher frequency. They don't, but it seems that way. The same would be true if the train was stationary and I was running towards it. Okay? That would be no different than if I was standing still and the train was moving towards me. As the two objects are moving towards each other, we call that a blue Doppler shift. It means that the frequency gets higher. Okay? The frequency we hear gets higher. If the two objects are moving away, then we have a red shift. Okay, a red Doppler shift, that means we hear a lower frequency. And it's actually the Doppler effect that has led us to conclude that the universe is still in a state of expansion. right? When we look at distant objects with X-ray telescopes and things like that, we notice that their wavelengths tend to be shifted towards the red end of the spectrum as opposed to the normal end of the spectrum for objects that are closer to us, which would imply that they are moving away, and thus the universe must be expanding. Okay? It's the Doppler effect that's allowed us to conclude that that is in fact the case. Now, we're not going to see red and blue shifts in light, right? Like a car's headlights don't look blue as they approach you and red as they go away, okay? And I'm not saying that, you know, yeah, they've got the HID lights and then I'm looking at the tail lights, obviously that's blue and red, but okay, if I'm standing still and looking at some headlights and then I run towards the car, they don't look bluer while I'm running towards the car, okay? We can't go fast enough to make a significant change in Doppler effect for light, because light is a short wavelength, it travels extremely high speeds, we can't go fast enough to really see that. If we had things that were capable of going near relativistic speeds, near the speed of light, we would see that. Okay? We would see them shifted towards the red if they were going away, or shifted towards the blue as they move towards. Okay. All right, is that making sense? Yes? All right, so the bunching up, okay, causes, again, that change in frequency that we perceive. Okay. This is basically this, we've talked about all this already. So what we need to look at now is the formula for the Doppler effect. Okay, this is probably one of the trickier ones for us to use in terms of manipulation. Okay, the true Doppler effect formula. I'm just going to borrow your sheet here because I always use the wrong F's. F and F0. Right? Okay. So the true Doppler effect formula looks like this. Okay. Now, in your formula sheet, it doesn't look like that. This is the true Doppler effect formula. Okay. The Doppler effect formula says that the frequency that is heard, okay, so this is the perceived frequency, okay, is equal to the original frequency okay, times this ratio. Now, the V's that are in here, okay, go as follows. This V, these two V's are the same, okay, V without any letter after it, is the speed of sound. Okay, this is the speed of the observer. This is the speed of the source. Okay, so the things that affect the frequency I hear, or the Doppler frequency, or the shifted frequency, okay, the things that affect that are the speed of sound, and my speed, and the source of the sound speed. Those are the three things that can affect it. Now, Alberta Learning decided a couple of years ago that you do not, for some reason, have to do Doppler shift problems that involve a moving observer. So they changed the formula. So the formula on your formula sheet does not have this stuff on the top about the observer. It just has the speed of sound on the top. That's it. Okay? It doesn't require us to do this. I don't know why they did that, because it doesn't really make the questions any harder or easier, but that's what they decided. Okay? Now, I've got plus or minus here. Now, this is the first time we've had a formula that said, you might need to add it or you might need to subtract it. How do I decide? Evan? Right, if it's moving away from me or if it's moving towards me is going to determine whether I add or subtract the speed of the source. All right, so here's what we have to think about. If the sound is moving, if the source, is moving towards me, this number is bigger than F0, right? I hear a higher frequency of sound if the source is moving towards me. Everyone okay with that? right, so the only way for the Doppler frequency to be bigger than this is if whatever's in brackets here ends up being bigger than what? Not 0, bigger than 1. Okay? If I multiply this by a number bigger than 1, f will be bigger than f0. Everybody okay with that? All right. So if what's in brackets needs to be bigger than 1, am I going to add or subtract in this operation? Subtract. Okay, here's why. I'm taking these two v's are the same number. Okay, so I'm taking this number and I'm dividing it by the entire bottom. I want the entire bottom to be smaller than the top so that it comes out to a number greater than 1, and then my f will be bigger than f0. All right, so you might want to make a note of this somewhere. Okay, but we subtract for an approaching source. Which means then that we add for a retreating source. Because if I add those two numbers together, the bottom of that equation will be bigger than the top, and I'll get a decimal. And if I multiply by a decimal, the number will get smaller. Okay? Everybody following me mathematically there? All right. Now, let's look at manipulation of this formula, okay? Because it can be a little bit tricky. Okay, I want to solve for f0. How do I do that? Right now I'm multiplying f0 by what's in brackets, and I want to have f0 by itself. Yeah, divide f by this entire thing, right? I mean, if I do order of operations, I figure out what this is before I multiply it by this number, so I can just divide the whole bracket over to the other side. Okay, so I would just divide v over v plus or minus vs over to this side. That would give me f0. That's the easiest manipulation. Okay, now if we're using this formula and they want us to solve for vs, that's a little bit trickier. Now, the other thing that's worse is solving for v, but you don't have to. Okay, you don't have to solve for v. It's in two places. Okay, so you'll never be asked to solve for the speed of sound using the Doppler effect formula. Okay, so you won't ever have to solve for v. But if I want to solve for vs, okay, then what I need to do is do first some manipulation. First, I should move f0 over here, okay, because that'll eliminate the need for the brackets. Everybody okay with that? All right, so I'm going to divide both sides by f0. So now it's gone. Now I have f over f0 equals v over v plus or minus. Let's just say we've got a retreating source, so we'll say plus, okay, vs. Okay, I want to solve for vs, but it's on the bottom of the equation. What can I do to get it to the top? I could, but that's going to mean I've got to move a whole bunch of other things around again. No, I don't want to change to a negative because this is a retreating source. It has to be positive. Okay, remember that the rules of algebra say this. I can do whatever I want to an equation as long as I do it to both sides. Yeah, flip it. I can do whatever I want to an equation as long as I do it to both sides. So that's what I'm going to do. I'm going to flip this. I'm going to say that f0 over f equals v plus vs over v. Now vs is on the top. Now I can solve for it. Okay, so I'm going to multiply both sides by v. Okay, so I've got FOV over f, okay, equals v plus vs. Then I just need to do what with this? Subtract it over. So I'll end up with FOV, okay, over f minus v equals vs. Right? Does this change if I'm subtracting vs? It can change. Okay, so let's have a look at how that might change. Okay, all the other steps are going to be the same up to this point. Okay, just now I have V minus Vs. So if I subtract V over to the other side, I'm solving for negative Vs. And as long as I remember that, that's okay. Okay, I just have to recognize that when I do this calculation, I'm going to get a negative number, okay, and I shouldn't. Or I can do this. I can add Vs over to this side, and then subtract this over to the other. Okay, so I'd have Vs equals FOV over F. Sorry, I did that wrong. V minus FOV over F. Okay, it's not terribly tricky. Okay, but it's a little different than anything else we've done, okay, in terms of manipulation. Okay, is that making some sense? All right, let's have a look at what some of the problem solving might look like for this. All right, I've got a train traveling at a speed of 30 meters per second. Now, what often gets people in a Doppler effect question is not being able to tell which frequency is which. Okay, you have to read the question very carefully so you don't get the frequencies mixed up. Okay, so the train is traveling at a speed of 30 meters per second. Which part of the equation? Sorry, here's the equation again. Which part of the equation is that 30 meters per second? Vs. It's the speed of the source. Okay. All right, its whistle generates a sound wave with a frequency of 224 hertz. Okay, you are standing beside the tracks, important, beside them, not on them. Okay, the train, as the train passes you with its whistle blowing, so that means I was standing beside the tracks and the train was coming towards me. Do I add or subtract? I subtract. Okay, so again, reading the question carefully, okay, is an important part of getting one of these right. Okay, what's the change in frequency? What change in frequency do you detect as the whistle of the train as the train passes if the speed of sound, so that's V, equals 330 meters per second? Okay, which F did they give me? They gave me FO, right? Okay, that's the frequency of the whistle, not the frequency I heard. They want to know what frequency I hear. Okay, that's F. So they gave me FO. It's 224 hertz. All right, so good news is, for this problem anyway, I don't even have to manipulate. All I had to do was decide whether I was adding or subtracting. All right, so F will equal 224 hertz times 330 over 330 minus 30. Okay, so standing beside the tracks, I would hear a frequency of 246 hertz. Okay, slightly higher than the actual frequency of the train's whistle. Okay, I want you guys to try 1 and 2 here. The answers are down below. Watch out for dirty tricks. Do I want the speed in kilometers per hour? No, sir. Okay. All right, give those ones a try. Okay. They use in the book, they use true frequency. I always use original or actual. True also means F0. Okay, so the true frequency is F0. Okay, so for number 1 here, okay, we're crossing a crosswalk, an approaching driver blows his horn. If the true frequency of the horn is 264 hertz, okay, so they gave us F0. Okay, and the car is approaching you at 60 kilometers per hour. Right, so we got to convert that to meters per second to get the speed of the source. What did that come out to? What was that in meters per second? 16.6. Okay, meters per second. Okay, what is the apparent or Doppler frequency of the horn? So we're looking for F. Okay, and we know that the speed of sound is 340 meters per second. All right, so this car is approaching me. So in my formula, I'm going to want to add or subtract. Subtract, right? Okay, so I'm going to have V over V minus Vs. So that's going to look like this. 264 hertz times 340 divided by 340 minus 16.6, right? And when I do that, I should get 278 hertz as my Doppler frequency or shifted frequency. Okay. All right, how many people have done number 2? Okay, do we need to go over number 2 as well? Yes, no, yes? We need to go over number 2? Okay, well, I assume we don't then. Okay, so you don't have to do number 3. That one's asking to calculate speed of sound in air, but I want you to try number 4. Okay, in number 4, you're trying to find the speed of the train. Okay, so I'll give you a few minutes on number 4 here. Okay, so on number 4, they tell us that we, as the train moves away from us this time, okay, the frequency of its whistle is determined to be 475. That means that's what I heard. Okay, so that's going to be F, 475 hertz. This question is not really very clear about which one is which, but what I have to do, Richard and Tanner, is I have to kind of read the context of the question. It says it's moving away from me, and I know if it's moving away from me, the one I hear is lower. Okay, so sometimes you just have to go with that if the context of the question isn't very clear. Okay, the actual frequency of the whistle is 500 hertz. Okay, so that's going to be F0. Okay, and then it tells us the speed of sound is 350. All right, so we're looking for the speed of the train as it moves away from us, or the speed of the source. Okay, so we're going to have F equals F0 times V plus Vs. It's moving away from me this time, so I'm adding. All right, so the first thing I'm going to do is divide both sides by F0 so that it comes over here. Then I am going to flip both sides. Okay, so I'm going to go F0 over F equals V plus Vs over V. Then I'm going to multiply both sides by V, and then I'm going to subtract this V. So what I'll end up with is F0 times V over F minus V equals Vs. So when I plug in my numbers, that's going to be 500 times 350 divided by 475. There's 475. Yeah, okay. And then I'm going to subtract from that 350. Okay, so when I do that, I should get 18.4 meters per second. Okay, questions on how those work? All right, I'm going to have you work on a couple off of the worksheet here, but I'll give you about a 3 or 4 minute break here before we get into that. Okay, so you can have a 3 or 4 minute break, and then we'll get working on those. Okay, so for number 3 here, okay, it's asking us how fast does the source of sound need to be moving if the observed frequency is 3% higher than the true frequency. So all I have to do is pick 2 numbers that are 3% different. So 100 and 103 will work perfectly. Okay, those are the numbers I'm going to choose for F and for F0. So the observed frequency is going to be 103 hertz. The actual frequency is going to be 100 hertz. And now I can work towards getting how fast that thing must go. Okay, is it moving towards me or away from me? Towards. That's the only way the observed frequency could be higher than the actual frequency. Okay, so we're left with F equals F0 V over V minus Vs. Okay, so we're looking for Vs there, so we'll have FOV over F minus V equals Vs, and we just plug in our numbers. So we'll have 100 times 340 divided by 103 minus 340. Okay, so we should get, I don't have an answer on there. So we should get 9.9 meters per second. Doesn't have to go very fast for a 3% change in the frequency. Okay. Any other ones? Okay, keep her going then.